Hello everyone, my name is Nana and I'm from the Bodhi Academy. So today we'll continue with the part of structure of atom. In today's video we'll see about the developments leading to the Bohr's model of atom. In that we'll see the wave nature of electromagnetic radiations, particle nature of electromagnetic radiations, that is Planck's quantum theory, photoelectric effect and dual behavior of electromagnetic radiations. So this developments leading to the Bohr's model is basically because of the Rutherford's model. So it gave the lead for Bohr, that is Niels Bohr, to propose his idea regarding the structure of atom. So results observed from the studies of interaction of radiations with matter have provided immense information regarding the structure of atoms and molecules. Okay, so Niels Bohr utilized these results to improve upon the model proposed by Rutherford. There are two developments that played a major role in the formation of Bohr's model of atom, and these are the dual character of electromagnetic radiations, which means radiations possesses both wave-like and particle-like properties. Now, where did these radiations come from? As you know that Rutherford, he proposed a structure of atom like this. He said that there is a nucleus at the center, right, which consists of protons and neutrons. Around this nucleus, he said that there are orbits. Yes or no? Around this nucleus, there are orbits. In this orbits, he said that there is electrons revolving around. So this is what Rutherford proposed. He said that there is a nucleus and this nucleus consists of protons and neutrons. And the electrons are revolving around it, just like a solar system, right? Where nucleus is the sun in the solar system and all the planets revolving around it are represented as electrons. But there is one thing that Rutherford could not explain, that is, in a solar system, around the sun, all the planets they revolve. Since planets do not have any charge, it revolves like that only. But here, these electrons are negatively charged. When a charged particle revolves continuously around in an orbit, it starts to emit radiations. And then eventually it will emit all its radiations and fall into the nucleus, which will form the Thomson's model. What Thomson said? He said that an atom is made up of positively charged particles, that is protons, are evenly spread. And in these protons, he said that the electrons, okay, they are present embedded inside them, just like watermelon structure. Okay, in watermelon, what happens? The red color part of the watermelon is considered to be the positively charged part of the Thomson's model, and where its seeds, the seeds of watermelon, are considered to be the electrons. So, when these electrons in Rutherford's model, it start emitting the radiations, it will eventually fall into the nucleus and form a structure like this. So, both the cases, it cannot explain the stability of the electron. Later he said that it is stationary, that the electrons doesn't move. But that also has an effect. So if electrons were stationary, electrostatic attraction between the dense nucleus and the electrons would pull the electron towards the nucleus to form a miniature version of Thomson's model. So in that experiment, it was discovered that there is a release of radiations, and this radiation later it is named as electromagnetic radiations. Okay, and it is said that electromagnetic radiations possess both wave-like and particle-like properties. Now, experimental results regarding atomic spectra, which can be explained only by assuming quantized electronic energy levels. So this part regarding the quantized electronic energy levels, we'll see in this chapter only in the next part. Okay. So let's first start with the dual nature of electromagnetic wave radiations. So first we'll see the wave nature of electromagnetic radiations. So what it was given by James Maxwell. He was the first person to give a explanation about the interaction between charged bodies and the behavior of electrical and magnetic fields. So he was the first person to explain the interaction between a charged particle and its behavior with electrical and magnetic fields. So he suggested that when electrically charged particle moves around, moves under acceleration, alternating electrical and magnetic fields are produced and transmitted. So what he said, when a charged particle, for example, electron is negatively charged. So when it moves, it will produce and emit. Transmit means produce and emit. Will produce and emit electrical and magnetic field. That is alternating electrical and magnetic fields is produced. So these fields are transmitted in the form of waves. And he said that whatever electrical and magnetic field is transmitted, it is transmitted in the form of waves. And these waves are known as electromagnetic waves or electromagnetic radiations. Okay. Light is the form of radiation known from early days. So light is considered to be a form of radiation in the earlier days, and speculation about its nature dates back to remote ancient times. And since light was considered as radiation in ancient times, how these lights are moving? It is moving in a particle form, wave form, what type of thing it is was started in that speculation was started in the remote ancient times. So in earlier days, Newton means light. Okay, they said instead of light, they used to say Newton. So light was supposed to be made up of particles. So in earlier times, they considered that light or Newton was supposed to be made up of particles. Particles, they named it as corpuscles. Okay, so it was only in the 19th century it was discovered that it has a wave nature. Okay, light has a wave nature, and this was also given by Maxwell. Okay, James Maxwell was the first one. Again, he is the first one to reveal that light waves are associated with oscillating electric and magnetic character. So that is one. It is said ki it is dual nature, right? And here also we have seen ki it is alternating electrical and magnetic field. So once it will send an electrical field, then it will send a magnetic field. So similar thing here. It is because of the oscillating electric and magnetic character. So it will show electric as well as magnetic in alternating form. So although electromagnetic, that's why it is a electromagnetic, electrical and magnetic wave. So electromagnetic wave motion is complex in nature. We will consider here only a few simple properties. So it is a complex thing. We will have only some simple properties of those waves. Okay. So first one is the oscillating electric and magnetic fields produced by oscillating charged particles are perpendicular to each other, and both are perpendicular to the direction of propagation of wave. What is says the particle, charged particle is oscillating, right? So due to these oscillations, it is sending electric and magnetic fields. So the electric and magnetic fields are perpendicular to each other. Perpendicular means if this way is electric field moving, then example, there are three parts. No, if this is the electric field, if this way is the movement of electric wave, then this will be the magnetic field, and both are perpendicular to the direction of propagation of wave. So if this is the direction of propagation of wave, this way is the direction of wave, then this will be the electric field and this will be the magnetic field. Both are perpendicular to the direction of wave. Okay, if or the particle that is moving, charged particle, if it's moving in this direction, then the radiations emitted are in the perpendicular way. I'll explain it with this red line is the propagation of particle. Okay, in this way is the charged particle moving. Hmm. Then this will be the movement of electric field. In this direction will be the electric field. This will be the magnetic field, or in this direction will be the magnetic field. And both this electric and magnetic field, these are emitted from a charged particle. So if this black dot is a charged particle, and along this red line is its movement, along this red line is the movement of the particle or the propagation of the wave. From this charged particle, due to its movement, it starts giving out electric and magnetic field. So this green part will be your electric field. In this direction is the electric field. This is perpendicular. What is perpendicular means? This is a perpendicular line where it is straight to the line. So this we can consider to be perpendicular, and this is also a perpendicular. So both are perpendicular to the propagation of wave. So what it says, the oscillating electric and magnetic fields produced by oscillating charged particles are perpendicular to each other, and both are perpendicular to the direction of propagation of wave. So here I showed it how it will be. This is the exact diagram. So you can see this is the electric field and this is the magnetic field and this is the propagation of wave. So same thing I have shown it in your 2D form. Okay. Second point is what? Unlike sound waves or water waves, electromagnetic waves do not require medium and can move in vacuum. Now for sound waves, it requires a medium. Like there should be particles that should carry the sound waves. And for water waves, there are particles that are carrying water waves. But for electromagnetic waves, there is no need for, or it do not require any kind of medium. It can move in the vacuum also. Okay. So first point is what? Ki electric field, magnetic field and propagation of wave are all perpendicular to each other. Okay. Second point is what? Ki electromagnetic waves, they do not require any medium for their movement. They can move in vacuum also. Third point, it is now well established that there are many types of electromagnetic radiations which differ from one another in wavelength or frequency. So now we have a range of electromagnetic radiations which differ from one another in wavelength. What is wavelength? So this is the wave. So this length is the wavelength. So each of them differs in the wavelength. This constitute that this constitute what is called as electromagnetic spectrum. And since we have many types of electromagnetic radiation which differ from one another in wavelength, we had made, or it is made simple to identify which are the waves using an electromagnetic spectrum. So they have made an electromagnetic spectrum to reduce the, or to make it easy to identify the waves. So different regions of spectrum are identified by different names. So there are different names for each of the spectrum. So some examples are radio frequency region around 10 raised to 6 hertz used for broadcasting. So you know that there are radio waves, right? So there is which carries the radio transmission. Then there is a microwave region which is 10 raised to 10 hertz used for radar. Radar means on the radar system. There is infrared region used for heating and all. There is ultraviolet region. Ultraviolet radiations or ultraviolet UV lights are in sun's radiation. So ultraviolet is a sun radiation. The small portion around 10 raised to 15 hertz is what we call as visible region. So there is a visible light which we can see through our naked eyes. So it is only this part which our eyes can see or detect. So visible light is the only part that we can see. So special instruments are required to detect non-visible radiation. So there are special instruments which are used to see the non-visible radiations. So there are different kinds of units are used to represent these electromagnetic radiations. So these radiations are characterized by the properties namely frequency and wavelength. So all these radiations they are differentiated, or this now I told you different radiations, right? Like radio wave, microwave, infrared radiations, ultraviolet radiations, visible light. So all these radiations, they are characterized on the basis of frequency and wavelength. So they are frequency and wavelength change. There are different frequencies and wavelengths for all these different things. So according to this, they are characterized. The SI unit of frequency is nu, is hertz. We frequency, it is symbol is nu and its unit is hertz. Hertz is Hz. Okay. After Henry Hertz. So this unit was given after this scientist, that is Henry Hertz. So it is defined as the number of waves that pass a given point in 1 second. So it is basically Hertz is basically the number of waves that pass a point in 1 second. If I'm keeping a detector here, how many waves pass through this detector in 1 second? That is what hertz is. Okay. So wavelength should have the units of length, and you know that SI units of length is meter. So wavelength should have a SI unit of length, right? This wavelength. So it is meter. So SI unit of length is meter. Since electromagnetic radiations consist of different kinds of waves of much smaller wavelengths, smaller units are used. So it consists of smaller wavelengths, right? There are small to big wavelength. So we use smaller units. Okay. So here shows various types of electromagnetic radiations which differ from one another in wavelength and frequency. So this is a spectrum, electromagnetic spectrum of electromagnetic radiation. So it starts from long radio waves, which is till 10 raised to 6, 10 raised to 8 we can consider. This is radio waves, right? So there is AM and FM radio waves. These are long radio waves till 10 raised to 5 we can consider. 10 raised to 6 to 10 raised to 8 is the AM and FM radio waves. Then here we have microwaves. So it is long radio waves, FM radio waves, microwaves, IR, and in between IR and UV. Okay, in between IR and UV, this part is the visible range. So this is the visible range. Here it is. This is a visible spectrum. So between IR and UV is the visible spectrum. After UV, we have X-rays and gamma rays. These are long radio. These are shorter waves or has shorter wavelengths. So in vacuum, all types of electromagnetic radiations, regardless of wavelength, travel at same speed. So at vacuum, all these radiations, that is the X-rays, gamma rays, UV rays, IR rays, all these rays or all this radiation in vacuum, they travel at same speed regardless how long, how short their wavelength are, they travel at same speed, and that is 3 into 10 raised to 8 meters per second. Okay. And if I want to tell you in precise means this is a rounded off number. In precise, it is 2.997925. So it is rounded off to 3. Okay. This is called the speed of light. And this value, that is 3 into 10 raised to 8 meters per second, is the speed of light and is given by symbol c. Okay. So it is written as 3.0 into 10 raised to 8 meters per second. And this is small c. This is value of small c. So a small c value. Small c means speed of light. The frequency nu, wavelength lambda, and velocity of light is c. Okay, this is the velocity of light are related by an equation. So all these terms, that is frequency, wavelength, and velocity of light, it is related to each other by an equation, that is velocity of light equals frequency multiplied by wavelength. Okay, so it is c is equal to nu lambda. Wavelength, it is represented by lambda. So the other commonly used quantity, especially in spectroscopy, is the wave number. Okay, along with wavelength, there is a wave number. That wave number is represented like this. So this is the wave number V. There is a dashed line on top. So it is defined as the number of wavelengths per unit length. So how many? It is the number of wavelengths. How many wavelengths are there in a unit length? So its unit is reciprocal of wavelength, that is per meter. So wavelength's unit is meter, and for wave number it is per meter. It is a reciprocal, that is for wavelength it is meter, and for wave number it is 1 upon meter. So in short, we can write it as meter raised to -1. So however, common unit is centimeter. It's not a SI unit, but a smaller unit of wave number. Particle nature of electromagnetic radiations. What are the particle nature of electromagnetic radiations? And these are known as Planck's quantum theory. So this is explained by a theory. So some of the experimental phenomena such as diffraction or interference can be explained by the wave nature of the electromagnetic radiation. Now what is diffraction? What is interference? Interference, you know, right? Something is extra or something is there which is not required. So there is a diffraction, interference. These properties can be explained by wave nature of electromagnetic radiations. So following are some of the observation which could not be explained with the help of even the electromagnetic theory of 19th century. So at 19th century, whatever electromagnetic theory was given, these are few points that cannot be explained using that theory, now known as classical physics. It is known as classical physics. Okay, the first point is the nature of emission of radiation from hot bodies or black body radiation. So what is black body radiation? Any radiation that is emitted from the hot bodies, hot materials. What are those radiations? How are those released? If this part is not explained by the electromagnetic theory. Ejection of electrons from metal surface with when radiation strikes it, that is photoelectric effect. We'll see what photoelectric effect is. Okay, that time I'll explain this point. So variation of heat capacity of solids as a function of temperature. So there is variation in heat capacity of solids. So each solid require various temperature. Why it is like that? Line spectra of atom with special reference to hydrogen. So there is a line spectra that is in the other part. Okay, that is in the quantum theory, quantized particles. So that time I'll explain this point. Okay, about the line spectra. So it is noteworthy that the first concrete explanation for the phenomena of the black body radiations was given by Max Planck in 19th. This phenomena is given below. So about regarding the black body, that is the heated particles or hot bodies, was given by Max Planck, and that is explained here. So let's see, when solids are heated, they emit radiations over a wide range of wavelengths. For example, so when any solid is heated, they emit radiations over a wide range. For example, if a solid is heated, it will start emitting radiations in all directions, right? So when an iron rod is heated in a furnace, it first turns to dull red and then progressively becomes more and more red as the temperature increases. For example, an iron rod. A rod, if you burn it or if you keep it in the heat, if you heat it in the furnace, first it will turn a dull red, it will be a light red. But as you keep on heating it, it will progressively start to become more and more red. It will become dark, shiny red when the temperature increases. So as this is heated further, the radiation emitted becomes white and then becomes blue as the temperature becomes very high. So when this rod is heated, continuously heated, first it will start become red, then it will turn to dark red, then to a white color, right? At last it will become a blue, it will become a bluish color and the temperature becomes high. So in terms of frequency, it means that the frequency of emitted radiation goes lower, okay, as the temperature decreases. So similarly, when heat is increased, the radiations emitted will be faster. So the frequency of those will be very lower. So they will go down the frequency range to higher frequency as the temperature increases. So starting, if the frequency is 2 waves per second, then as you increase the temperature, it can go up to 10 waves per second. So as the temperature increases, the frequency also increases. So the red color lies in the lower frequency region. So you know that about the rainbow, right? With your region. So red is the lowest one. So red color lies in the lowest frequency region, while blue color belongs to the higher frequency region of the electromagnetic spectrum. So the ideal body which emits and absorbs radiation of all frequencies is called black body. So what is a black body? It means a body, an ideal body which emits and absorbs radiation of all frequency, all type of frequencies. They can emit as well as absorb radiations. All frequency means what? When it is just heated, starting stage of heating, it will release frequency in a lower range. But as you go on increasing the temperature, the frequency also increases. So the radiation, so the body which can emit and absorb radiations of all frequencies is called black body. And the radiation emitted by such body is called black body radiations. Okay, so the exact frequency distribution of the emitted radiation, that is intensity versus frequency curve of the radiation, form a black body that depends on temperature. So black bodies usually depends on the temperature. So at a given temperature, okay, intensity of radiation emitted increases with the decrease of wavelength. Okay, so at a given temperature, the intensity of radiation emitted increase with the decrease in wavelength. That means if the wavelength is this big, but as you go on increasing the temperature, okay, the radiation emitted increases. So the radiation emitted will increase and it will increase in such a way that the wavelength will go on decreasing. Okay, it will become smaller and then starts decreasing further, decreases the wavelength and reaches a maximum value at a given wavelength and then starts decreasing with further decrease. So it will go on decreasing. So the above experiment results cannot be explained satisfactorily on the basis of the wave theory. So this, whatever I told you now about the waves, frequencies and temperature, it cannot be satisfactorily explained by the wave theory. So Planck suggested that atoms and molecules could emit or absorb energy only in discrete quantities and not in a continuous manner. So what he said, ki all the atoms and molecules, they can emit as well as absorb radiations at a fixed or at a particular quantity, not in a continuous manner. It will reach a point where it won't start to emit or absorb any radiations. Okay, a belief popular at that time. So this was what he said, and it was what everyone believed at that time. So Planck gave the name quantum to the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic radiations. So whatever emit radiation that can emit or absorb the smallest quantity, okay, the smallest quantity of radiation or energy that can be emitted or absorbed in the form of electromagnetic radiation, Planck named it as quantum. Okay, so the energy of quantum of radiation is proportional to the frequency and is expressed by E is equal to h mu. Okay, so this is the relation between energy of quantum of radiation, frequency, and h is the Planck's constant. So h is known as Planck's constant. And this Planck's constant has a value of 6.626 into 10 raised to minus 34 joules second. Okay, with this theory, Planck was able to explain distribution of intensity in the radiation from black body as a function of frequency of wavelength at different temperature. So this is how he explained about the black bodies. Okay, function of black bodies. Now, what is photoelectric effect? So, in 1887, Heinrich Hertz, okay, performed a very interesting experiment in which electrons or electric current were ejected when certain metals, for example, potassium, rubidium, or caesium, etc., were exposed to a beam of light, as shown in the diagram. So, what he did is he passed electrons or electric current, okay, a metal through certain metals, for example potassium will take. So this is a metal surface or a potassium surface. Through this metal surface, what he did is there was a light or the electrons, light energy that is passed. So this light energy, it is directly put on the metal surface, and from that metal surface, so a beam of light is passed on that metal surface, and it is shown that there is a release of electrons. Okay, and that electrons was detected by a detector. This chamber is vacuum chamber. Okay, so and this phenomena he called it as photoelectric effect. So what he did was he performed an experiment in which electrons or electric currents were ejected when certain metals, for example potassium, rubidium, caesium, etc., were exposed to a beam of light. Okay, the phenomena is called photoelectric effect. So the results observed in the experiments were, so when he exposed a beam of light to a metal piece, what were the results that he observed? He observed the electrons are ejected from the metal surface as soon as beam of light strikes the surface. So there is no time lag between the striking of light beam and ejection of electrons in metal surface. So the moment this beam of light touches the metal surface, an electron is emitted. So there is no time difference. The light strikes, electrons are ejected. Okay. So this was what he observed. So he observed that when the light strikes the metal surface, an electron is ejected with no time lag. Okay. Striking and ejecting both takes at same time. Okay. The moment the light strikes, an electron is emitted. Okay. Second point is the number of electrons ejected is proportional to the intensity of brightness of light. So how many electrons are ejected, that depends on the intensity or brightness of the light, how bright the light is. If the light is too bright, then the number of electrons emitted will be high. If it is low, it is dim, then the electrons emitted will be less. So it depends on the intensity or the brightness of the light. Third point is what? For each metal, there is a characteristic minimum frequency known as threshold frequency. Okay, V mu naught means threshold frequency, below which photoelectric effect is not observed. So there is a certain frequency. If the light is at that particular frequency only, then the electrons are emitted. If it is below it, then there won't be any photoelectric effect observed. Okay. So at a frequency, the ejected electrons come out with certain kinetic energy. The kinetic energy of these electrons increases with the increase in frequency of light used. Okay, so what is threshold frequency? It is the frequency required to remove the electron under a photoelectric effect. So all the above results could not be explained on the basis of law of classical physics. Okay? According to later, the energy content of the beam of light depends upon the brightness of the light. So how bright the light is, so that will depend, that will help to emit the electrons. So it will depend on the brightness of the light. So in other words, number of electrons ejected and the kinetic energy associated with them should depend on the brightness of light. So how bright the light is, that will decide the electrons ejection and the kinetic energy associated with it. So it has been observed that though the number of electrons ejected depends upon the brightness of light, the kinetic energy of ejected electrons does not. Okay, so the number of electrons ejected depends upon the brightness of light, but the kinetic energy of electrons ejected, that doesn't depend on the brightness of light. Okay, so the red light, okay, for example, red light of any brightness may shine on a piece of potassium metal for hours, but no photoelectrons are ejected. So when a red light is continuously passed on a potassium metal, for hours you can pass it, but there won't be any photoelectron effect. So there won't be any electrons that are ejected. But as soon as even a very big yellow light shines on potassium metal, the photoelectric effect is observed. So the threshold frequency for potassium metal is 5 into 10 raised to 14 hertz. So the threshold frequency of red, the frequency of red is 4.3 to 4.6. But the frequency of yellow light is 5.9 to 5.2. And threshold frequency of potassium is 5. So that's why when yellow light is passed, okay, there is a photoelectric effect that is seen. So Einstein in 1905 was able to explain the photoelectric effect using Planck's quantum theory of electromagnetic radiation as a starting point. So Einstein, he was able to explain the photoelectric effect of Planck's quantum theory. Okay. So what he did is there was a shining beam of light on a metal surface. Okay, therefore be viewed as shooting a beam of particles, the photons. So he named those beam as photons. Okay. So photon of sufficient energy strikes an electron. So the beam of light, he named it as photons. It is said that beam of light contains a beam of particles and those particles are photons. So when a photon of sufficient energy strikes an electron in the atom of metal, it transfers its energy instantaneously to the electron during the collision and electron is ejected without any lag or delay. So it is said that the electrons that are ejected because when the beam of light strikes that electron, it is the photon that is striking the electron and that photon is transmitting its energy to the electrons and that is why it is ejected out. Okay. So greater the energy possessed by the photon, greater will be the transfer of energy to the electrons, and greater the kinetic energy of ejected electron. So the kinetic energy of electron, or the speed at which it moves, it is basically because of the energy of photons. So if photons has higher energy will be transferred to electrons, and that will increase the kinetic energy. Okay. So in other words, kinetic energy of ejected electrons is proportional to the frequency of electromagnetic radiation. So it is proportional to the frequency of electromagnetic radiations. What? Kinetic energy of an ejected electron. So since the striking of photon has energy equal to h mu, or that is Planck's constant into frequency, and the minimum energy required to eject the electron is h mu naught, also called work function W naught. So this h mu naught is threshold frequency, so also called as work function or W naught. So then the difference in energy, that is h mu minus h mu naught, is transferred as the kinetic energy. The kinetic energy of photoelectron can be given as h mu minus h mu naught. For conservation of energy principle, the kinetic energy of the ejected electron is given by h mu equals h mu naught plus 1 by 2, that is half of me v square. So where me is the mass of electron, v is the velocity associated and with the ejected electrons. Lastly, a more intense beam of light consists of larger number of photons. So consequently, the number of electrons ejected is also larger as compared to that in an experiment. Okay. So in today's class, we have seen about the photoelectric effect, then particle nature of electromagnetic radiations. We have seen Planck's quantum theory. Then we have also seen the spectrum of electromagnetic radiations. What is the wave nature of electromagnetic radiations and developments leading to the Bohr's model of atom. So in our next class, we'll see the dual behavior of electromagnetic radiations and some terms associated with it, that is quantized electronic energy levels, emission and absorption spectra and all. We'll see then the line spectra of hydrogen. Okay, all these points we'll see in a next class. So thank you for watching my video. Please do like, share and subscribe to our channel.